here. So again, from regular iOS, if we go to the BGP process, let's say router BGP1, and we're going to issue a network statement for a directly connected loopback. So on router 1, this is 1111. Mask is /32. From router 2, we're going to do the same thing. So let's say under router BGP1, the network is 2222. Mask is /32. And then the same thing on our other iOS boxes, which are router 8 and router 10. So router 8 is in BGP process 8, network 8888, with a mask of /32. And same thing on router 10. Okay, router 10's on the bottom there. Network 1010, 1010, mask is /32. Okay, then last but not least under XR, basically the same thing here, but when we look at the show run router BGP, where would we guess that the network statement is going to go? So we have two different options. We could either apply it globally under BGP under the AFI, or the AFI under the neighbor. It really depends. Are we trying to apply an attribute that applies to all neighbors, or are we trying to apply it to a specific neighbor? In this case, it's general to the overall process. So the network statement is going to go under router BGP and then under address family IPv4. When we go to apply a policy change, the policy change would be under the particular neighbor. But just to originate the route, we're going to go to router BGP1, address family IPv4 unicast, and then issue our network statement. Okay, in this case, XR1's loopback is 11.11.11.11/32. Okay, if we show config, we can see where specifically that's going in the hierarchy is under BGP, under the AFI, and then under the specific network statement. Okay, once this is complete, if we look at the show BGP, and we want to know what is our specific address family identifier, you can see that by default, when you look at just the show BGP in iOS XR, this is the equivalent of saying show IP BGP in regular iOS, means we're talking about the regular global routing table. But anytime we're talking about a more specific AFI, like if we want to look at IPv6, VPNv4, we need to say show BGP, what is the address family identifier like IPv4, what is the sub-address family identifier like labeled unicast, and then we could say a specific prefix, or we could just say for all routes. So we'll see what does labeled unicast mean a little bit later, but specifically this AFI would be IPv4 unicast. Okay, if we were to compare the output here of iOS XR to regular iOS and just show IPBGP, we can see the output is fairly similar, where the key attributes that we're looking for here is whether the route is a best path. So it's going to be that greater than sign. We can see what is the specific prefix and the prefix length, what is the next hop value, and then what are the different attributes of the route. So what is the multi-exit discriminator, what is the local preference, what is the weighting, and then what is the autonomous system path. Now, before we get to that point that we can worry about any of the BGP attributes, we need to make sure that the BGP route is actually valid and that we're installing it into the BGP table, which means we can install it into the routing table, and then ultimately means we can install it into the forwarding table, like the CEF table, to actually forward the packets. Now, from the output that we have here under iOS XR, one of the things that we should notice here is that we don't have the route to router 8, who is, or actually we don't have, when do we not have to router 8? Router 8 may be, let me make sure that that address exists. The address does exist. If we show IPBGP, router 8 is advertising the route, but from XR1's point of view, it is not receiving the route. And this is what I was referring to before, and what that log message that was generated on XR1 tells us, that for eBGP peers in iOS XR, you must apply the routing policy language to allow prefixes in and to allow prefixes out. So it's kind of like a default protection mechanism that says if you don't define the RPL, then I don't know whether you actually want to receive these routes inbound. And regardless of whether the policy just says we want to permit everything, we still need a policy in place that says we can just pass the routes or simply allow the updates in. So before we go any further, let's go ahead and make that change. And specifically, the way that we're going to do this is to go to global config and define a route policy. And we'll say this is to pass all, is the name of it. And we simply want to pass the routes. Okay, so pass means that we're going to allow it, and then it can continue on for further processing. The other option we could have said would be to say we want to done. Accept this route with no further processing. Okay, in our particular case, they would have the same effect. Okay, we then exit out of the RPL. If we now look at the show RPL or the do show RPL. Okay, right now we haven't committed the config, so let's say show config. Those are our uncommitted changes. The candidate config, we save the changes. Then we show RPL. We can see that the policy is now created. Now, we still need to apply the policy, and if we look at under the BGP hierarchy, where would we specifically apply this? When we show run router BGP, this would not be an option global to the BGP process. This would be an option on a per neighbor basis, because this is how we effectively change attributes, affect BGP policy application, like change a local preference, do ASPath prepending, do community tagging. We're going to be doing that on a per peer basis. So this means that we're going to go under the BGP process, we're going to go to the neighbor 10.8.11.8, and we're going to go to the address family. So address family is IPv4 unicast. And then we're going to say we want to apply a route policy. And how are we going to apply this? The route policy pass all is going to be applied outbound, and it's going to be applied inbound. Okay, we'll look at more detailed application of this later, but if we look at the show config, what this is essentially saying is to allow all updates out to the neighbor, allow all updates inbound. Now, before we actually apply this change, there's one other way that we would have known that there is an issue with this policy application, is if we were to look at the show BGP IPv4 unicast summary, and we'll see that next to this particular neighbor status, it has this exclamation at the end. And it says, we will not be receiving any routes or sending any routes to neighbors that are marked with the exclamation. And it basically means the problem is that you didn't apply your routing policy, so the default routing policy is drop for eBGP, not allow as it is in regular iOS. So once we commit the config, then we look back at the BGP summary, we should see now that we're receiving the prefixes from the neighbor. Okay, the end result is if we show BGP, IPv4 unicast, okay, we can see now we're receiving the update in from router 8. Okay, the end result is if we look at the show route IPv4 for BGP, we can see we have router 8's loopback installed. And if we look at this from router 8's point of view and look at the show IP route BGP, we see that we have the loopbacks of 1, 2, and 11. So in terms of transport, we should now have connectivity from router 1 to router 8 or from router 2 to router 8, as long as we're sourcing those packets from an address that we actually advertised into the BGP table. So from router XR1, if we ping 8888 and source this from loopback 0, we should see that we have IP connectivity. Now, the rest of the devices, if we were to do the same thing on router 2 and router 1, whether we actually have connectivity or not is going to depend on some additional updating behavior, some additional next hop behavior of the BGP process. And we'll see that this behavior is very, very key to understand how it works between different address families. Because if we can't advertise the routes or we can't learn the routes or we can't use the routes, then ultimately we're not going to be able to forward traffic to the final destination. And what I mean by this is that the advertisement rules of the actual updates change depending on what type of peer that you have, whether it's an eBGP peer versus an iBGP peer, if your IBGP route reflector is a client versus a non-client. And then beyond this, the next hop processing rules are going to change depending on what type of peer that we have and also depending on what type of address family. Now for this example here, we're going to focus just on IPv4 unicast, and we're running IBGP as a full mesh between the neighbors. And we'll come back a little bit later and look at other variations in terms of doing IBGP route reflection, IBGP confederation, and see how the processing rules are going to change. But the key as we have it now is that from XR1's point of view, we are learning updates inbound from an eBGP neighbor, and then we are passing them to an IBGP neighbor. Now there's no restriction in terms of can we advertise the route or not. The default behavior is that we will take eBGP learned routes and advertise them to IBGP neighbors. But the key reason here that router 1 and router 2 don't have reachability to the destination is that when we look at the show IPBGP, we're learning the update, but we're not installing it as a best path. And if we look at the show IPBGP for 8.8.8.8, it says the reason we're not installing the update is why. Because the next hop is inaccessible. So specifically when we look at the attributes of the route here, it says we have the prefix and length, so the actual route is 8888/32. The next hop value is 10.8.11.8, and it's being received from the neighbor 11.11.11.11. Their router ID is 11.11.11.11. It came from IGP. This means that someone originated with the network statement. Multi-exit discriminator is 0. Local preference is 100. It came from an IBGP neighbor. But the key here is that we don't know how to reach the next hop value. Now, the reason this is the case is that when we take this eBGP learned update, and this is specifically when we're talking about the IPv4 unicast address family, we'll see this behavior changes later when we're dealing with VPN v4 unicast. So the route's coming in from an eBGP neighbor. We're then sending it to our IBGP neighbor. We do not change the next hop value. Router 1 sees the next hop is router 8's connected interface. But since we're not running an IGP between XR1 and router 8, and also because we're not advertising that link into our internal routing protocol, okay, in this case is IS to IS, router 1 is basically saying that if I were to install this route in the routing table, the issue is going to be that I don't know how to reach the next hop, which ultimately means I won't be able to do the route recursion process, and I won't be able to actually forward traffic to the final destination. So essentially, as a protection mechanism to not advertise routes that you don't have reachability to, BGP says that if the next hop is inaccessible, you cannot use the route as a best path. And if the route is not a best path, it implies you cannot install it in the routing table. It also implies you cannot advertise it to other peers. Now, we'll see that there are multiple solutions to this particular problem, that we don't have the route to the next hop, but mainly it's going to be one of two variations. That either we need to give them a route to the next hop, or we need to change the next hop to something that they already know. So in this particular case, we're going to look at it in both variations. We'll say from XR1 to router 1 and 2, we're going to simply change the next hop of these updates so that we're using our local loopback. And then router 1 and router 2 are saying, well, as long as I know how to get to 11, 11, 11, 11,